Okay, excuse me. We're going to continue on where we left off last time, which was towards the end of chapter 4. And last time we talked about some things, chemistry, like atomic numbers, I believe, which again is our number of protons. We have our mass numbers, which is our number of protons plus our number of neutrons. Remember that both of those numbers are important because, again, if you kind of subtract both of those numbers, the mass number from the atomic number, that will get you your number of neutrons. Also important to remember, as we talked about, the only one that you find on the periodic table there is the atomic number. And again, that is the number that we see up on top. And as we talked about last time as well, obviously the number of protons, which is the atomic number, is really the most important thing in terms of what element you're dealing with, as none of the elements repeat their atomic number. So every element has its own individual atomic number and number of protons. So really, if you know that, then you do know what element you're dealing with. You'll know based on the number of protons are the atomic number. Also, a reminder that the mass number is not on the periodic table. And once again, that number on the bottom, which we will talk about shortly in one of these chapters coming up, maybe 8. And that number is the atomic mass, which is different than the mass number. And again, the way you can remember that, as we talked about, which is when you do calculate the mass number, atomic number, protons, electrons, neutrons, they all do need to be all positive whole numbers. And again, if you look on the periodic table, pretty much all the atomic masses are decimals, so they are definitely not whole numbers. So you want to make sure that you get that correct. We talked about the periodic table, right? And with the periodic table, right, we talked about several things, including groups and which way groups go, right? Groups going up and down. There's different ways in terms of the groups, in terms of their numbering. But pretty much in every chemistry class that you take, we pretty much use the A numbering, which is the representative numbering. And that is group 1, where lithium is. Remember, hydrogen is not part of group 1. But lithium is to start. Beryllium, group 2, we do skip and pick back up where boron is, and that is group 3, 4, 5, 6, 7, and 8. We do skip sort of that middle section between those two in terms of our groups. Also, periods, right? Periods go left to right on the periodic table. There's 7 periods. And we have periods going from here, like I said, left to right as well. We also have special names for our groups, right? So group 1 is the alkali metals. Group 2 is the alkaline earth metals. Group 7 is the halogens. Group 8 is the noble gases. Also, elements are broken up. There's sort of that staircase by boron coming down. They are broken up into metals, which are good conductors of heat and electricity. They're also very shiny. Thank you very much. Upper right of that staircase, that is where we find typically our nonmetals, and they're pretty much the opposite characteristics. They're dull, they're brittle, they're bad conductors of electricity, heat and electricity. And really on that staircase is our semi-metals, our metalloids. And these are guys that have properties that really do fall sort of on either side of where they're located on the periodic table. The same metalloid could have some properties that would be considered more metal type properties, and the same one could have some properties that would be considered more sort of non-metal type properties. And it does make sense as you kind of go left to right there. You are transitioning from metals to non-metals as you kind of go upwards. That part that we skip between group 2 and group 3, those are our transition metals. And again, we'll talk more about those in naming, but they do usually have the ability to make a variable type of charge. For example, copper could be +1 or +2, as opposed to other sort of metals which have more fixed type positive charges. With that, we also talked about, with atomic number and other things, ions. And again, a reminder, there are cations, which are positively charged, And we talked about how we get there, and that basically is from losing electrons. So when somebody loses an electron, they have more protons than electrons. So they have more positive charge than negative charge, and that will end up being more positive. And anions are negatively charged, which is a result of them gaining electrons, and sort of the opposite there. Pretty much they have gained electrons, so they have more negatively charged electrons than positively charged protons, so they will end up with a negative charge. Remember that the number for the charge, be it positive or negative, represents really how many electrons are involved, either how many electrons were lost or how many electrons were gained from the neutral element in that case. Most of the time, as we'll talk about there, metals are guys that will lose electrons. Non-metals are the ones that will gain electrons. And that's typically what will happen, is actually we'll go this way. The metal will typically give the electrons to the non-metal, and that's how come they will make an ionic compound when we put them together. We talked a little bit at the end there, again, about naming as well of these guys, just simple ones. So cations, we pretty much just use the whole name of the metal. And for anions, those are the guys that kind of have the non-metal name. And then we drop the last part and we put IDE there. And again, sometimes we drop a little bit more than the last part of the name. So for example, oxygen becomes oxide, chlorine becomes chloride when they have a negative charge. And again, nothing from the periodic table has a charge until they sort of hook up with like metals and non-metals get together. That's when things really do start to get charges. Any questions on any of that stuff there that we were talking about last time there? All right, so to continue on with sort of our talk of ions there, a reminder that, and we'll see this again when we talk about naming, but there are certain elements that do have fixed charges. And starting here in group 1, pretty much everybody in group 1 will form a +1 charge when they do form a charge. Group 2, that's going to be a +2 charge. Once again, we do skip here the middle part, and we go to group 3. And really in group 3, I would say aluminum is pretty much your element there that's going to form +3. They do include these guys on the chart here, but they could also form some other charges sometimes. So really aluminum there for group 3. Right here where boron is, again, we got that staircase kind of coming down. And going up from the right of that staircase is the nonmetals. So we do skip group 4 as there's no real good pattern. But group 5, they tend to form -3. So +3 here. Group 6 -2 and group 7 -1. Once again, we're talking about the nonmetals here above the staircase. So for example, nitrogen and phosphorus is pretty much what we're talking about here. Remember, kind of below the staircase, those are actually metals that have positive charges. So above the staircase are nonmetals where they will have these negative type charges. For the most part, transition metals, as I mentioned before, can have a variety of charges depending on who it's hooked up with and all that kind of stuff. There are, though, 3 transition metals that, even though they are transition metals, they will form pretty much a fixed charge. And that is this 3 right here. That is zinc, and below it, cadmium. Hang a left over to silver. Silver, when it makes a charge, will be +1. And both zinc and cadmium, when they make a charge, will be +2. So those 3 are sort of exceptions for the transition metals. Even though they are transition metals, they kind of have fixed charges. And no matter what happens, that's going to be the charges that they form. Once again, as I mentioned, things do not have charges until they start interacting really with metals and nonmetals on opposite sides of the periodic table. Any questions on that there? All right. So let's talk a little bit then about ions and what happens when we have ions and sort of where we find ions. Just so you know, where we typically find ions in most cases are floating around in solutions. So floating around in solutions is typically where we would find something like a sodium ion, maybe a chloride ion kind of floating around in the solution part of it as ions. They are typically aqueous ions. And they typically will have that little kind of symbol next to them, the AQ, which stands for aqueous, means a water environment. It means basically a solution, and basically they're floating around kind of in the solution. So when you do put something, say, in water or dissolve something in water, and it has the ability to break apart into ions, those are things that are referred to as being electrolytes. And electrolytes are substances that when they go for a swim in water will dissolve basically and break apart into ions. And the breaking apart into ions is really important with electrolytes because that's what gives electrolytes the ability to conduct electricity. So electrolytes can conduct electricity because of the presence of those ions, the positive ions floating around, the negative ions that are floating around. Those ions that are moving around help kind of complete the circuit, complete the charge, and allows it to be really sometimes a very good conductor of electricity. Now, when we talk about electrolytes, there's a few different types of electrolytes that we come across. So let's talk a little bit about those. The first one's a strong electrolyte. And with a strong electrolyte, it will 100% break apart into ions in solution. So, for example, if you had a sodium chloride solution, it would break apart into sodium ions and chloride ions. And what you would have in that solution is 100% these ions floating around. You would have none of these units still together. So if you looked at that little beaker, you basically would have nothing but sodium ions floating around, chloride ions floating around. You would have none of the sodium chloride whole unit still together. Basically, it's just going to break apart. And because of that, you basically in that solution have a ton of ions just floating around freely. And that is the perfect conditions for an electrolyte. And this thing will conduct electricity really, really well. So for example, years ago, they used to do an experiment where you take a light bulb with some electrodes on it. And if you stuck the electrodes into a strong electrolyte solution, the light bulb would turn on and be very, very bright. So it would conduct electricity really, really well. It'd be able to power like the light bulb just from that. So it can conduct electricity very well. Got bright light. Now, there's also weak electrolytes. And weak electrolytes will break apart into ions in solution. But the difference is it actually will mainly stay together. So for example, if you took hydrofluoric acid, which is HF, it's actually a weak acid and a weak electrolyte. When it breaks apart, it'll break apart into H plus and F minus. And the difference is when this kind of is in solution, what you mainly have in that solution is you mainly still have the whole thing together. It hasn't really broken apart. You will produce a little of these guys here. And that means when you look at sort of the beaker for that there, you mainly have those HF units still floating around, no real ions. You got a little bit of some F minuses and H pluses floating around, but not a tremendous amount. So because it still is able to produce a few ions floating around in solution, it is still considered an electrolyte. It can actually still conduct electricity. So this guy can conduct electricity, but nowhere sort of near as much as, say, a strong electrolyte. So if you were to take that light bulb example and you stuck those electrodes into a weak electrolyte, the light bulb would come on, but it'd be very, very dim, almost like it's dying, basically. It kind of looks like it's got just enough juice to kind of turn on just a little bit, and it'll look really, really dim. So it'd be very dim, the light there, if you did that. One way you can recognize sometimes a weak electrolyte or this situation is the arrows that you see here. And these are arrows that are heading in both directions. This implies that this reaction is actually a reversible reaction. And that means there's two directions. There is reactants to products, which is our forward direction. And eventually what will happen in these type of reactions is you'll make enough products that they will actually start heading in the backwards way and head in the opposite direction. And those products will recombine to make the reactants, which is what is referred to as the reverse direction. It will eventually reach what is referred to as equilibrium, which means the rate of the forward direction and the rate of the reverse direction will equal each other. And essentially what happens when you reach equilibrium is everybody just locks into place. So just as quick as you lose a little this way, some come back the other way. So it's kind of like a nice balance. You don't actually have equal amounts on both sides of the arrow, but once it reaches equilibrium, pretty much wherever everybody is, they will just maintain exactly their concentrations where they're at because there's really no overall change that's occurring. That's also the topic of 1B, the entire class. It's all about equilibrium. Everyone, you never want to learn. You will learn in Chem 1B, but that's the idea there. Any questions on that there? Now, the last type of electrolyte, it's actually a non-electrolyte is called. So a non-electrolyte will dissolve in water, for example, but will not produce ions. And it's really that lack of ions being produced, which means it actually will not conduct electricity. And again, it has really no ions present to do so. An example of that is sugar. So if you took some sugar, it's going to dissolve. But sugar is covalently bonded. It doesn't, when it dissolves, break apart into ions. Just the whole thing dissolves all at once as one sort of unit. So because it doesn't produce any ions, it will not conduct electricity. So if you go back to our light bulb example, if you stuck it into a non-electrolyte, the light bulb pretty much won't turn on. It'll basically just be dark. It won't have light up at all. It won't be dim or anything like that. Water, for example, pure water is a good or bad conductor of electricity. Pure water is actually a bad conductor of electricity because there's no ions in it if you have pure water. Clearly, the shower and the water coming out of your pipes is not pure water. They actually put ions in it to clean it, which means you will electrocute yourself. Yes, you try to blow dry your hair in the shower or something like that, right? So you don't want to do that for sure. But if you have pure water, because there's really no ions present, it's actually a bad conductor of electricity, but obviously it's a good conductor. In our situations, usually because they put ions in there, or there's usually ions dissolved in it. And that's what we see here. Again, this would be what you would see with a strong electrolyte. The presence of all those ions is going to allow it to really light up that light bulb really well. Here in a non-electrolyte, no light bulb happening. And obviously a weak electrolyte would be in the middle of those, kind of a dim light bulb would turn on. Again, because there's a little bit of ions present, but it's mainly going to stay together in terms of a weak electrolyte. Any questions on electrolytes there? Now, we talked about ionic compounds last time, and I think we also touched upon that when we do put ionic compounds together, anything that is a positive ion with a negative ion, they obviously have an attraction to each other, and that's what's known as electrostatic attraction. That's that opposites attract, right? So things with opposite charges are attracted to each other. This is basically what salt looks like or sodium chloride looks like before you dissolve it. There are sodium ions and chloride ions stuck together, basically, and they are maximized by trying to get those positive negative interactions away from negative being near each other or positive. The chloride here, which is the negative guy, is larger in the picture because it has gained electrons, right? So its electron cloud gets larger, so it gets larger. Here, the sodium ion is actually smaller because it has lost electrons, so it shrinks overall in terms of its electron cloud. What happens when you go to dissolve this is you take some water, and basically a bunch of water molecules just surround each of those ions and pop them off basically from each other. So what ends up happening, for example, is you have positive ions that get surrounded by waters. You also have negative ions that get surrounded by water as well. by the way, the opposite side of water for the negative guy is actually the hydrogen is attracted to it because hydrogen is more positive in water, and the oxygen is actually attracted to the positive ion because it's more negative actually in water. So that's what happens in that case. You help this along a lot by when you go to dissolve something, you stir it, right? So you stir it, you throw a bunch of water molecules all over that thing, and also throw some energy in there, and that helps it dissolve. It doesn't really go anywhere. That's a physical change, right? And it doesn't go anywhere. We just can't see it because there's so many water molecules. It just kind of disappears from our vision, basically, because there's a lot of water molecules when you have water involved. We know it's still there, like one of those earlier experiments you did where you had salt water put in the evaporating dish. Once you start heating it back up, the salt water, all the water molecules evaporate, which now means there is no obstacle between those two ions from coming back together. And that's why you see the salt return at the end once you evaporate it off. Before that, the water molecules are allowing it to dissolve and also keeping those ions, which are strongly attracted to each other, away from each other. They act almost like a buffer without letting them get to each other. But once you evaporate it off, like you put it on your evaporating dish and you heat it up, all the water molecules evaporate, nothing in the way of those ions from popping back together, and the solid reappears at the end. Any questions on that there? Now, when we do add a positive ion and a negative ion together, as we probably touched upon last time, we do want to make sure that overall the charge of the ionic compound formula is equal to 0. And we want to make it equal to 0 in the simplest way possible. So, for example, obviously here we have our sodium ion and our chloride ion. So when we would put these together, that's a +1, a -1. All we need is one of each. That will get us to an overall charge of 0. When you write the formula for an ionic compound, it should never have a charge. When you write the formula for ions, they should have charges. So when you put them together, we want no overall charge when you put a positive guy and a negative guy together in the ionic compound. But individually, if you're just writing ions, they actually do have charges. And this thing, although it does not have any charge shown, is actually made up of two ions. It's made up of a sodium ion and a chloride ion. So it's actually made up of two things that have ions in it. If we take our calcium, which is +2, and our chloride, which is group 7, -1, and we go to put this together, we cannot just put them together like they are. Otherwise, we will end up with a charge. So to balance it out, you could just multiply the two numbers together. 2 times 1 is 2. And you would just need one more chloride here. 2 Cl minuses gives you a -2 to balance out the +2. And really at that point, you can just count what you got. 1 calcium and 2 chlorides, CaCl2. Remember, the subscript goes to the guy to the left. And again, if we have 1, we don't write 1 usually. So the name of the guy on the left here, whole name for the metal, sodium, right? IDE for this guy, chloride, right? Whole name for the metal here, calcium. And IDE for this guy, which is chloride. You do not use any type of prefix in this situation. And we'll talk more about it when we officially talk about naming, but definitely when there's a metal and a non-metal involved, which is usually an ionic compound, you never ever use a prefix. It doesn't matter how many you have. That is basically how you name it. Whole name of the first guy, the positive guy, IDE for the second guy, and you're good to go. Now, sometimes people will be taught you should just, drop these charges down and that'll give you the subscripts. And frankly, you could do that blindly if you want, but it will work about 93% of the time. So if you're good with that and you want to miss 7% of the time, you can do that or just blindly do that. But I would more think about balancing out the charges this way. That way you'll get the right formula. So there's definitely a lot of situations where if you just kind of not think about and drop the guys down or even take the guys back up to get the charges of the ions, you will get the wrong answer. So it does work over 90% of the time, I would say, but it doesn't work all the time. So here we have barium, which is +2, oxygen, which is -2. So really in this case, we just need one of each of those to get to 0. We'll talk about why we really need 0 in this situation, but just to kind of preview it for you, it's actually the bonding aspect of it is why we actually need these guys to basically equal 0 in the simplest way possible. The simplest way possible when these guys equal 0 allows everybody in this bonding situation to have the correct number of electrons. Basically, it gives everybody a stable situation in terms of their electrons, and that's why we're really doing it. Here with aluminum, which is +3, and sulfide, which is -2. Once again, if you multiply the numbers together, that is 6. So to get aluminum to 6, I need 2 of them. To get this guy to 6, I need 3 of them. That's -6 plus 6. That's 0. At this point, you can just count what you got. That is 2 aluminums. And that is 1, 2, 3 sulfurs. And that will give you your right formula in this particular case. And obviously here we have K plus and phosphorus there, or phosphide, which is 3 minus. You could even do 3 times 1 is 3. That tells you you actually need 3 of those guys. And that gives you a +3 to balance out the -3. And our formula here, 3 Ks and 1 phosphorus in this particular case. In terms of the names here, this is barium oxide. This would be aluminum sulfide. And this would be potassium phosphide. Again, whole name of the first guy that's positive, IDE on the last one. Any questions on that? There's obviously more rules to naming than just that, which we'll get into when we talk about naming, but that's generally metal, non-metal, how you roll with it, whole name of the metal, IDE for the non-metal. That is definitely how you name any compound that has a metal from group 1, 2, or 3. If there is a metal from the transition metals region, you got to do a little extra work with that, but it is mainly the same type of naming. Any questions on that there? All right. All right, that wraps up chapter 4. We're going to roll into chapter 11 next. Okay, so in chapter 11, we're really going to talk a lot about electrons and really electron configuration. And we're going to talk about really overall this kind of idea of what happens when we have different energy levels and you have an electron, say like this arrow representing the electron, and you excite the atom or do something like you did when you did flame tests, right? You put that element or atoms into the fire, it gained a lot of energy. What's going to happen is these electrons are going to jump to a higher energy level. And one of the things that we know about energy in chemistry is we do not want to be high in energy. Really, everything that happens in chemistry, for the most part, is basically to try to reduce down the energy as low as possible. And that's really the most sort of stable idea or version of things. So eventually what will happen is this guy will work his way back down to a lower state of energy, may not even come back down to where it started, but it will try to come down. But with the law of conservation of energy, we don't lose or create energy along the way. So in order for that electron to come down, the atom itself, for example, would have to give off some energy. And that energy would be in the form, as we'll talk about here, as, say, a photon of light. Now, for example, if that photon of light coming off has a wavelength that is like the same as, say, in the visible part of the spectrum, where we see colors, we would see colors. That's kind of what happens with fireworks. When they launch up the fireworks, they explode them. And obviously that excites all the electrons in those elements. They come back down to a lower energy level, and then we go, ooh, red, blue, green colors, right? We see all these different colors that basically come off when that occurs. So we're going to talk a little bit about modern atomic theory. And as we talked about in the last chapter, really our atom, right, is a center core that is positively charged, which is our nucleus. It has our protons, which are positively charged. It has our neutrons, which have no charge associated with it. And outside in that empty space, which is a majority of the atom, is where the electron cloud is. And we have our electrons moving, again, randomly about the nucleus. As we talked about, there is an attractive force between the nucleus, which is positively charged, and the electron, which is negatively charged. But they are moving those electrons, again, in a pretty random sort of pattern. We don't really know exactly how they're moving, where they're located, which we'll talk about why that is a little bit later on in this chapter. But they do not move in pretty little circles or anything like that. So early on, a guy by the name of Planck, who was a physicist, came up with this idea that when he heated a lot of solids, he would notice that atoms and molecules would emit energy in whole number multiples. And he sort of referred to that as sort of a quanta of energy or a quantum of energy. And the idea of a quantum of energy and sort of relationship to what we're talking about in this class is this idea, as we'll talk about when we're talking about sort of those electrons that are transitioning from different energy levels. If we have an electron, say, on this energy level down here, it would gain enough energy, for example, to fully transition all the way up, say, to that energy level. Or if it was working its way back down, it would give off a certain amount of energy sufficient to make it all the way down to the lower energy level. It would not sort of find itself in between. And that's the idea of quantized energy. It's kind of the, we'll see a better picture of this later, but it's kind of the staircase example, if you will. When you're walking stairs, you have enough energy to get to this step, this step, this step, and this step. Or if you're coming down, obviously, you have enough energy to make it, all the way down the step, for example. You don't typically walk up a step and go, I'll just stop halfway between the steps, right? Because you'll fall. And that's sort of the same idea here. You have enough energy to fully transition from one step to the next. Some people can maybe do 2 steps at a time, right? Up or down, maybe 3. I don't know more than 3, but and the same thing with electrons. Electrons will either gain or lose enough energy to fully transition from one energy level to the next. And again, that could be several energy level transitions. It could be just one energy level transition. But again, they will not find themselves kind of halfway between or gain or lose enough to just halfway make it. They're going to either fully make it up or down to a specific energy level. Bless you. And that is the idea really of sort of quantized energy, which is what we see with electrons. Now, to understand sort of Planck's idea, we have to talk about radiation, and radiation is really the emission or transmission in space of really energy in the form of waves. So as it's doing this transition, energy is being given off basically in the form of a wave. And waves do have some characteristics associated with it. And let's talk a little about some of those characteristics in a second. But a wave can be thought of as a vibrating disturbance in which energy is transmitted. So obviously, if you've ever been in the ocean, right, you've been through a wave, right, and you can see it coming, and sometimes it crashes on you, right, with a lot of energy. But if you're there, you could actually sit in one place like the bird there, and the wave will pass you, right? So you see the big wave coming, you just kind of go up with it, right, and let it go past you as you're in the water. And waves do travel through space this way, and depending on the wavelength associated with it, it may have very high energy associated with it. It may have very low energy associated with it. And again, depending on where it falls in the electromagnetic spectrum that we'll talk about as to what you might witness or see. So some of the parts of a wave here, we have the wavelength, which is lambda. And the wavelength is really the distance between 2 peaks or troughs here. And it is lambda, and that is the wavelength. And it's usually expressed in meters, centimeters, and nanometers. I would say for the most part, meters and nanometers are very common units that you see associated with these type of calculations. For example, a reminder that our friend nano is 10 to the minus 9. So a lot of, like, for example, the visible part of the spectrum where we see colors like the red, orange, yellow, green, blue, indigo, violet, those guys are typically given in nanometers. Everything else, for example, radio waves, microwaves, those guys are given a lot of times in meters as the units for the wavelength. So I would say meters and nanometers, definitely the 2 popular units. Centi every so often, again, centi was that to the minus 2, I think, right? So 100 centimeters in a meter as well. The frequency is nu, which is this symbol here. It is not really a V, although a lot of people call it a V. But it is the frequency, and that is the number of waves that pass a particular point per second. And the units of frequency are usually reciprocal seconds, which can be written 1/seconds, are s with a -1. And a relationship in terms of frequency that's also very important is a hertz. And a hertz is equal to a reciprocal second. It's basically a one-to-one relationship. So for example, your radio, right, when you dial it to like 95.5 megahertz, that is the frequency of the radio station, right? And that is also mega for hertz, as well as a very common sort of unit sometimes you'll see for frequency, mega to the 6, I believe. Amplitude is the distance from the main line there, the peak, if you will, to the halfway through to the bottom. And we can actually calculate the speed of a wave in general as the wavelength times the frequency. So if we take the speed of a wave, the wavelength is typically in meters. The frequency is typically in reciprocal seconds. So typically when we look at a speed of a wave, the units that we look at are meters per second. We'll see a little bit later on a more universal one where we don't use this sort of U. We actually use C, which is the speed of light, is the wavelength times the frequency. So that is very often the one that we use for electromagnetic radiation type waves. C is equal to the wavelength times the frequency. So typically, if you're going to use it in an equation like that, the wavelength typically needs to be in meters, and our frequency does need to be usually in reciprocal seconds or hertz, which is really the same thing for everything to cancel out correctly. Any questions on that there? So light behaves like electromagnetic radiation, which is that emission of energy in the form of waves. Electromagnetic radiation sometimes have properties that are very characteristic of particles. And a lot of what we talk about with sort of this quantum theory here is the idea of like the dual nature of light. So waves can have functions that are very similar to particles, and particles could be thought of as having wave-like function. They could just be like a stream of particles, basically acting as a wave. And something like an electron, for example, can have properties that are very much like a wave type function, which is why we'll talk about later on in this chapter why they move at very random sort of ways, and they don't move in really sort of nice, pretty circles and stuff like that. So sometimes, again, it's referred to as the dual nature of light, that wave particle nature. Again, waves could have particle-like function, and particles like electrons could have wave-like functions. When we think of a beam of light that is traveling, we could think of it traveling through space as tiny packets of energy, which are referred to as photons. And the relationship between wavelength and energy and frequency is this. If we have something that has a longer wavelength, like this, a little bit more drawn out, if you will. So we have a much longer wavelength. When we have a longer wavelength, it actually will have a lower frequency. It's going to take a little bit longer for it to kind of pass that point. And that typically results in lower energy. So something with a longer wavelength typically is associated with lower energy. And that's different than if we have a wave that is a much smaller wavelength, like so. With a smaller wavelength, it has a higher frequency and usually results in higher energy. As we will see shortly on this sort of spectrum, things with really, really small wavelengths are very, very high in energy. And things with much longer wavelengths are much lower in energy. And even things like color, as we will see in a second, the different colors have different energies associated with them as they have different wavelengths associated with them as well. So here is yellow light, and again, it can behave as a beam of light like a wave. It also can be thought of as sort of a stream of photons or packets of energy sort of coming through space. Here's an example of red versus blue. And we can see when we look at the red wavelength, it has a much longer wavelength, which means in comparison to red to blue in terms of color, red actually would be lower in energy. than blue, which would be higher in energy. Actually, the colors that we can see, right, is the Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And towards the violet part there, where blue, indigo, and violet, towards the violet side, they have a much shorter wavelength and much higher in energy in terms of a color. And red, on the other hand, is a much longer wavelength, much shorter in color. So why would we see, for example, one versus the other? So if you just think about just logically speaking, if you had an electron that transitioned, for example, all the way from up here, all the way down to here, that is like in my bad picture here, 1, 2, 3, 4 energy levels. That's a pretty big amount of energy that has been transitioned. That means that that's going to be a lot of energy, which means it should have a short wavelength or a long wavelength, the energy coming off. It would have a short wavelength, right? Short wavelength, longer energy. So that might be something more of like the violet type color or purple or blue, as opposed that if you had an electron to start it here and just transition one energy level down, that's not a lot of energy, right? So that's going to be a much smaller amount of energy. And that might result from us being able to see something more like a red type color coming off and from that electron transitioning. So you can make almost like an educated guess in terms of it's a big energy, small energy, as to what color you might expect, or if you know what color you see, you can see how many energy levels perhaps it might be transitioning versus the other one. Any questions on that there? Now, like I talked about before, all this electromagnetic radiation or waves, they do share how fast they move, and that is the speed of light. And at this school, they like you to remember this number rather than the rounded 3 times 10 to the 8. So I guess we'll roll with this number here. That is 2.9979 times 10 to the 8. That is the speed of light. About 186 miles per second. That's pretty fast. Yeah. And that is a constant value that obviously you do need to know. And you do need to remember that that is a value that you oftentimes have available to you, but most often never given to you in a problem. So, if you're doing a problem, you like, what, I'm missing something. That might be what you're missing. Again, they just assume you know it, and it's very rarely sort of mentioned at all in a problem or anything like that. When we want to calculate something like wavelength or frequency, that is the equation that we see. C is equal to the wavelength times the frequency. And as I mentioned before, meters for our wavelength, reciprocal seconds for our frequency gives us meters per second for our speed of light. The good news on this one is it's pretty much the same rearrangement, which means if I want the wavelength, that is C divided by the frequency. Or if I want the frequency, that is C divided by the wavelength. Once again, C is our constant right here. That means if you know the frequency, you can figure out the wavelength. And if you know the wavelength, you can figure out the frequency of light associated with that through that calculation. Any questions on that there? Why don't we try one here? What is the frequency in reciprocal seconds for a wave that has a wavelength of 4.68 times 10 to the minus 7 meters? And pretty much this is going to be probably the equation that you might want to use here. We obviously have the wavelength given to us, which is 4.68 times 10 to the minus 7 meters. We are looking for the frequency. And as I mentioned a second ago, very common, no mention of speed of light here. But again, that is a value that they just assume that you know. And we are using the 2.9979. Yeah, I have to look it up myself because I remember 3 to the 8, to be honest with you, but we would just use this one. All right, so in this case here, we're going to have this and this. So we can solve for the frequency, which is C divided by the wavelength. And once again, in this case, our units for our wavelength, it's okay. We don't have to do any type of conversion because it's going to cancel out okay with our speed of light. But this, again, is why you do need really your wavelength in meters so that it will cancel out correctly with the speed of light. So if you have in some other unit, you got to do that conversion to do that correctly. So putting in our numbers here, we'll go 2.9979 times 10 to the 8 meters per second divided by our wavelength, 4.68 times 10 to the minus 7 meters. And we'll pop that in there, 2.9979 to the 8 divided by 4.68 to the minus 7. Going to give us 6.41 times 10 to the 14. Now, in terms of units, the meters on top cancel and the meters on the bottom cancel. That does leave you 1 over seconds as our units, or you can write the units as s to the minus 1 as well, whichever way you want to kind of do that. It is also the same thing as a hertz because it is a 1-to-1 conversion as well. Yeah. Any questions on that there? All right, let's try another one then. Here we're looking for the wavelength in nanometers. If we have a frequency of 5.6 times 10 to the 14 hertz. So why don't you take a moment there and see what you come up with. Now, what we got, we are looking for the wavelength in this case in nanometers. We do have the frequency 5.6 times 10 to the 14 hertz. Again, we could use our equation. C is equal to our wavelength times our frequency, where C again is our constant 2.9979 times 10 to the 8 meters per second. Once again, a reminder that 1 hertz is 1 reciprocal second. So really this is 5.6 times 10 to the 14 reciprocal seconds, which might be helpful to see sort of the units cancel. Solving for our wavelength here, we want to divide that to the other side. That's going to give us C divided by our frequency. Putting in our number, 2.9979 times 10 to the 8 meters per second, divided by our frequency of 5.6 times 10 to the 14 reciprocal seconds. That is going to get us basically 5.35 times 10 to the minus 7. In terms of units, the seconds and the reciprocal seconds will actually cancel, and we will be left in meters at this point. Once again, obviously, you want to make sure you're using your exponent button when you punch that in. First off, any questions so far on that? We then want to convert it now to nanometers. A reminder that nano is 10 to the minus 9. That would mean that in 1 nanometer, which is the prefix unit, there is 10 to the minus 9 meters, or 1 times 10 to the minus 9 meters in this case. We could do a little dimensional analysis type of move. So 10 to the minus 9 meters on the bottom, so they cancel. 1 nanometer up on top. Once again, that is 1 times 10 to the minus 9. That's going to give you 535 nanometers. We're looking a little sig fig action since 5.6 only has 2. Maybe we take it to 540 in that case. Yeah. Any questions on those calculations there? Okay, so obviously you need to be able to calculate the wavelength from the frequency, frequency from the wavelength, obviously nanometers, meters. You do need to, again, know the speed of light we talked about will not be provided for you, so make sure you know that 2.9979 number there. Any questions on that there? Okay. So as we're talking about this sort of transition of these electrons from different energy levels, again, the atom is either most likely going to give off energy in the form of a photon of light that has a specific wavelength. And depending on sort of where it falls on this electromagnetic spectrum here as to what you, again, might witness. So as we talked about before, the relationship between sort of wavelength and energy is the larger the wavelength, the smaller the energy. So over here, this is the wavelength of 10 to the 4 meters versus over here, which is 10 to the minus 12 meters. Over here on the left-hand side, that is a very small wavelength, which means in terms of energy, it should be a higher energy. also should be a higher frequency as well. As opposed to, say, over here on the right-hand side, that is a very long wavelength, which means it should have a lower frequency and also should have a lower energy. So we can see here on the right-hand side, we have radio waves, and that is low in energy, so it's why not too bad to listen to your radio in the car or whatever it may be. We go to the left there, we have microwaves, which has a shorter wavelength than radio waves, so a little bit more energy. So for example, it has enough energy to basically get your water molecules moving really fast, and then your pizza's cooked like in 2 minutes and stuff like that. We go next, we got 10 to the minus 4-ish. That is a smaller wavelength than microwaves. A little bit more energy is where we typically feel heat coming off in that case, in that infrared spectrum. Over here is the visible part of the spectrum. In the visible part of the spectrum, that is where we see colors. So that is where we see things like red, orange, yellow, green, blue, indigo, violet. So that's like our Roy G Biv, right? Coming that way. Sorry, that'd be a little early. And that is where we do see color basically happening here. And in this case, we can also see with the colors that there is differences in energy. So over here, that's basically 700 nanometers versus over here, which is 400 nanometers. And usually the visible part of the spectrum is given in nanometers. So over here at the red, that's going to be a lower in energy type of situation. Over here, as we talked about earlier, there in violet, going to be a little higher in energy. So again, even between the colors, there is differences in terms of the energy associated with it. Over here in the ultraviolet region, why we put sunblock on so we don't get too burnt, so a little smaller, a little higher in energy. Next is X-rays. That is typically why they put a lead vest on you and they walk out of the room when they give you the X-rays, so they're not being exposed to a lot of radiation. And gamma rays that we talked about in the previous chapter there, where we talked about alpha particles, beta, and gamma rays. Gamma rays is really just pure energy, is one of the strongest sort of emitters of energy. It's just very, very small wavelength, very high in energy. So if you ever use anything that's radioactive, that's a gamma emitter, you usually need a good amount of protection when you're using it because it is very, very high in energy. Now, in terms of the electromagnetic spectrum, you do need to know where all these things are, so you do need to know this. You do need to know it in the sense of being able to put things in order from, say, lowest energy to highest, longest wavelength to shortest, highest frequency to lower frequency. Any questions on that there? That also includes the colors. So you need to be able to put the colors in order based on those things as well. I don't know if I'll ask you exactly where, what wavelength they all break out at, but you do need to be able to kind of put those things in order. Yeah. Any questions? All right. So as we've been talking about here, atoms will basically absorb or release energy in these sort of quantized fashion. And again, allowing really something like an electron, as I've been talking about, to truly sort of fully transition from one energy level to the next. Again, they can move in both directions. Obviously, electrons, they can go higher in energy and they can drop back down lower in energy. And that still relates in terms of energy to exothermic and endothermic. So if the atom gains energy, that's going to allow those electrons to basically jump higher in energy, and that's going to be endothermic for the atom. As those electrons start to come back down in terms of energy, it's going to be exothermic for the atom. It's got to release that energy as those electrons transition back down. So we do see kind of both things happening here. Now, when we talk about a quantum of energy, we could actually calculate the energy associated with it by using this equation here, which is E is equal to H times the frequency. H is Planck's constant, and that's another number you should know, and that is 6.63 times 10 to the minus 34. Those are joules times seconds. So those are joules, which is energy, and seconds there. And frequency here is our normal frequency, which is reciprocal seconds. So if we look at units here, this is joules times seconds times 1 over seconds. The seconds cancel. It leaves us the energy in joules in this case. So when you use this formula, you will get energy in joules. So if you know the frequency of a wave that's coming off, you can figure out the energy associated with that photon of light. You also can tie this equation in with the one that we saw previously, which is our speed of light is equal to our wavelength times our frequency. And that is using our frequency as c divided by the wavelength. So if you take E is equal to H times the frequency and substitute in this for the frequency, you get E is equal to hc over the wavelength. So this version of that equation allows you to calculate the energy associated with a wave if all you know is the wavelength. You also can use this version of the equation if you know the frequency to figure out the energy associated with it. So if you know the wavelength or the frequency, you could actually calculate the energy associated with it. And that is because over here, H and C are both constants. So H is the Planck's constant on the bottom. C is the speed of light constant, that 2.99 number we've been using. And all you would need is the wavelength. The wavelength here, though, when you do go into it, does need to be in meters. So that properly cancels out once again with the speed of light, which is in meters. So you want to make sure, again, pretty much in most of these equations here, if you're using wavelength, you usually need to convert it to meters for everything to cancel out correctly. You just want to make sure you have it in that correct unit. Any questions on that there? All right, let's give it a try here. What is the energy in joules associated with a wave that has a wavelength of 465 nanometers? So why don't you take some time and see what you come up with here. Okay, so let's take a look, see how we're doing. We're looking for energy here. So energy is H, which is Planck's constant, times the frequency. In this case, we are looking for energy. We are given the wavelength, which is 465 nanometers. So we don't have the frequency. So once again, this is a case where we can apply sort of the earlier equation there and solve for frequency, which is c divided by the wavelength. And we basically can substitute that in, and that would give us E is equal to hc divided by the wavelength. Alternative to that, you could use this equation, get the frequency, and then put it in. It's just two-step process versus just doing it all together. But whichever way you want to kind of do it, you can. In this case, we do need to do a couple of things here. We do have C always available to us, which is our 2.9979 times 10 to the 8 meters per second. H, which is Planck's constant, also a constant, 6.63 times 10 to the minus 34 joules times seconds. Remember that when this wavelength goes in there, it does need to be in meters so that it cancels out correctly with our speed of light. Right now we're in nanometers, so we'll do that conversion first. Bless you, 465 nanometers. One of the nanometers is 10 to the minus 9 meters, or 1 times 10 to the minus 9. That's going to give us here basically 4.65 times 10 to the minus 7 meters in this case. Now that we have it in meters, we have basically all those things that we need here to get to our energy. So we'll go in there. We'll go with our 6.63 times 10 to the minus 34 joules times seconds for H. Our speed of light, 2.9979 times 10 to the 8 meters per second. And now our wavelength that's in the correct unit is 4.65 times 10 to the minus 7 meters. In terms of units, the meters on top and bottom will cancel. The seconds will also cancel. That's going to leave us just joules, which is good because that is our unit of energy that we are looking for in this case. All right, so punching out all of that in, making sure we are using our exponent button in this case. 6.63 times 10 to the minus 34 times 2.9979 to the 8, hit equals. Divide by 4.65 to the minus 7. Going to get us here 4.27 times 10 to the minus 19 joules as our answer in this case. Any questions on that calculation there? Yeah. So again, very common sort of conversion there, using the energy with the wavelength, because a lot of times you are given the wavelength rather than the frequency. As I said before, you could, in this case, use the C is equal to the wavelength times the frequency to get the frequency, and then just plug it into the E equals H times the frequency. Get the same answer, obviously, in that case, if you want to do it that way. Any questions on that there? All right, we're going to lay it up there right now.